Okay, so let's read about magnets and magnetism. This is Kingfisher, page 342 and 343. Follow along with me, and let's get started. Magnets and magnetism. Magnets can attract and repel each other over a distance through space because of their magnetic fields. The effect is called magnetism. Magnetism is named after magnesian stone from Magnesia, northern Turkey. So it's named after a place in northern Turkey. Over 2,000 years ago, the ancient Greeks found that pieces of magnesian stone attracted some metals. The stone was magnetite, a form of iron ore. A magnet is an object that behaves in the same way as magnetite. Some metals, such as chromium, become weakly magnetic when a magnet is placed nearby. This magnetism, which disappears when the magnet is removed, is called paramagnetism. Only 3 metals, cobalt, iron, and nickel, have the ability to become permanently magnetized when a magnet is placed near them and then removed. This property is called ferromagnetism. A bar magnet can attract, pick up, and support nails, paper clips, and other small objects made of iron, nickel, or steel. Steel is a mixture of iron with small amounts of carbon and other materials. Any piece of iron or steel can be turned into a magnet by stroking it several times in one direction with one end of a permanent bar magnet. When an object is attracted to a bar magnet, it sticks to its ends, or poles, where the magnetic field is strongest. One pole of a magnet is north-seeking and the other is south-seeking. The north and south poles of 2 magnets will attract each other. Similar poles, north and north or south and south, will repel, forcing each other away. So let's look at this picture down at the bottom of these 2 bar magnets. I'm going to read the stuff around this, and then I'll read the stuff over here. So here we're looking at these bar magnets. So these are little the picture has little iron filings between the bar magnets. That's just like little shavings of iron. Iron filings scattered around 2 magnets show the strong magnetic field between the north and south poles. This field pulls the magnets toward each other. So when you've got a north pole and a south pole on a magnet, they attract. They want to be together. But like in the second picture, if you have a north and a north or south and a south, they'll push away from each other. They repel. So when the north poles or the south poles of 2 magnets are placed near each other, they repel each other, push each other away. The force pushes out the iron filings. Okay, now I'm going to go up toward the picture of this little man. Physician William Gilbert, 1544 to 1603, was a doctor to English monarchs Elizabeth I and James I, and he introduced the term magnetic pole. The north and south poles of a horseshoe magnet point in the same direction. A bar magnet has a pole at each end. When it hangs on a string, it turns to point its north pole to the Earth's magnetic north. So just like how a compass works, the arrow on the compass wants to point to north. Here, a magnetic, where it turns, the magnet wants to point its north to the Earth's magnetic north. Some ring magnets have one pole on the outside of the ring and one on the inside. Others have one pole on each face. The lines of force of a magnet's fields can be seen by sprinkling iron filings onto paper around the magnet. The iron filings follow the lines of force, which are concentrated at the magnet's poles. The attractive and repulsive fields between 2 magnets can also be seen. That's what we talked about a while ago with these pictures. All right, and here let's look at this Earth picture. I'm going to read around it. Earth acts like a huge magnet with magnetic north and south poles, both of which are close to the geographic north and south poles. The compass needle points north to magnetic north pole, and there is a magnetic field. So Earth is guarded by this magnetic field, right? It's when things from outer space are coming towards us, which they don't really often do, or if they do, they're really small. But Earth has a magnetic field around it because of that magnetism running through the Earth's core and up to the magnetic north and magnetic south, and that field helps push things away from the Earth. All right. Oh, it looks like we're maybe talking a little bit about that in a second. Okay, magnetic fields. A magnetic field is the region around a magnet in which other magnetic objects can be affected by its magnetism. A magnetic object will always try to align itself with another object's magnetic field. The stronger the magnet, the larger its magnetic field. Earth has its own magnetic field, which is strongest at its magnetic north and south poles. The magnetized pointer of a magnetic compass aligns itself north to south and is a handy aid to navigation. Magnetism is a force that, although it is not fully understood, is put to use in numerous ways. Many machines, from car ignition systems to electric motors, make use of the properties of magnets. Video and audio tapes are coated with a thin layer of magnetic material. It is this material that allows them to be used for recording and playback. Magnetometers, this is down by the plane, are devices that measure the strength of a magnetic field. Towed behind aircraft, they can detect changes in Earth's magnetic field. Okay, up top, over by this picture of the Earth. Apart from enormous amounts of heat and light energy, the sun also pours subatomic particles. Remember our big 3 subatomic particles in an atom? Electrons, protons, and neutrons? Okay, so the sun also pours subatomic particles into space, most of which are electrons and protons. This invisible solar wind is electrically charged and affects Earth's magnetic field. The solar wind makes Earth's magnetic field lopsided. It extends much farther into space on the side of Earth farthest from the sun. The magnetic compass was first used around AD 1100. Chinese sailors used it to navigate when clouds obscured the sky. Homing pigeons orient themselves to Earth's magnetic field. Migrating birds, such as terns, use the magnetic field to find their way accurately over thousands of miles. Very cool. And then maybe next week, hopefully, we'll get to talk about electromagnetism, which is really crazy stuff, which is just one page over. So if you want to go ahead and read pages 344 and 345, you can, just in case we can't get to it next week. That way you can read it, maybe with a parent. You don't have to, but it's interesting, so you can. All right, have a great